My name is Areej. I am a PhD student at University of Waterloo, and I'm presenting semi-supervised affective meaning lexicon expansion using semantic and distributed word representation. And this is a joint work with my supervisor, Jesse Hoy. The problem that we are tackling in this study, that we are aiming to expand the relatively small affective meaning dictionaries with an up-to-date ratings of individuals or humans' annotations or emotions toward a wide range of terms. The manual annotation that is used by people or researchers in the field is slow, expensive, and labor-intensive, and it requires some expertise. And at the end, we will able to get like just a small number of annotated data. One of the limitations of this approach as well is that people's opinion changes over time. Terms like gay and homosexuality were perceived negatively up until the 21st century. Also, we need an automated method to annotate or get the EPA value of the new terms that constantly emerge in the social media. In the sentiment analysis field, several lexicon induction methods have been proposed to expand these human annotated lexicons. Their focus was on the one-dimensional lexicon valence or positive or negative lexicon. They have used three different machine learning methods: unsupervised learning method, supervised learning methods, or semi-supervised learning methods. The unsupervised learning method, as the name indicates, doesn't require any label data. It's based entirely on co-occurrence frequencies obtained from real-world corpora or from the web. To compute the semantic orientation or the sentiment orientation of a given word, we compute the difference between the strength of the association of this word with negative word and with positive words. For example, if we want to get the potency score of a word or a term president, we first get the co-occurrence frequencies of president with words that indicate high or positive potency and with words that indicate low or negative potency. And then given the number of hits or the number of the co-occurrence frequencies, we compute the difference of the strength of the association between these two numbers. Given this example, we can see that president will be it will have a very high potency. The unsupervised learning algorithms is very useful for many tasks, but the disadvantage of using such a method is that it's entirely based on co-occurrence frequencies, which sometimes noisy. Like, for example, word like movie will appear with like a negative or positive word all the time, and people will describe movies as bad movies, and people will describe movies as as good movies. So the rating of a word like that will be entirely based on the corpora that we are using. The semi-supervised learning algorithm, on the other hand, requires a large number of annotated data. It creates a feature vector of the word which is based on statistical, syntactical, or linguistic relationship between words. Using the feature vector and the annotation of the annotated data, we learn some decision boundary to label the unlabeled data. The disadvantage of this approach is that it's entirely based on the annotation of the annotated data. The semi-supervised learning algorithms requires a small set of label data. It builds a partially observed similarity graph that encode the similarity between the vertices, which is the word in the graph, and the edges will be the weighted edges will indicate the semantic distributed or distribution similarity between the words. The goal of the algorithm is to label the unlabeled node, giving the similarity with the other nodes in the graph. The algorithm will iteratively propagate the label from the labeled node to the unlabeled node, giving the weight edges. For example, the label of a node X will be at the end equal to the weighted average of its neighbors' current labels. To give an example of the label propagation algorithm, let's go back to the president. Using the similarity between president and premier, boss, and senator, which we already know that the EPA value for premier, boss, and senator, we can create a graph that represents the similarity between them. Here, the graph here represents the semantic similarities between these words, and giving this graph and giving the EPA scores of these words, or we could obtain the EPA value of president, which is not very positive, or not positive, not negative, and is quite powerful and not active. As we mentioned before, we built the graph based on the different similarities methods. The first one is the semantic lexicon-based label propagation, where in this approach we built the graph based on the semantic similarities obtained from two human annotated semantic lexicons, WordNet and Paraphrase database. These lexicon indicate or links words that they're similar, or they are synonym or hyponyms. The weight of the edge Wij in this graph will be 1 if xi is a synonym of xj, or it will be 0 otherwise. The count-based label propagation is based on the distributed hypothesis, stating that similar words occur in similar contexts. We obtain the co-occurrence frequencies from two different corpora. The signal media, which has like a 1 million news article dataset, and the North American news dataset. We created the co-occurrence matrices of these corpora on a window size of 4 words. We computed the smooth positive pointwise mutual information, and then we computed the truncated singular value decomposition. I'm not going to discuss these two things in details, but I discussed it in details in my paper. And the graph of this label propagation will be based on the cosine similarity between the singular value decomposition of the words in the vocabulary. We also tried the neural word embeddings label propagation. The neural word embeddings is a dense representation of word that obtained from training a neural network model or algorithm on a huge number of data set or textual information. We used two pre-trained word embeddings in this task: the skip-gram word vector model, which is trained on Google News dataset, and the global vector for word representation, which is trained on Wikipedia dataset. The weight of the graph, or the weight of the edges in the graph, is computed. Like for example, Wij here is equal to the cosine similarity between Vi and Vj, and Vi and Vj is the neural word vector of word I and j. For example, if in the Using the skipgram word vector, the edges, the weight of the edges between president and leader will be 0.46. We also combined the semantic and neural word embedding features. We computed the combination as a linear combination between the semantic similarity between two words like I and J, and WB here is the cosine similarity between two neural word embeddings I and J. And eta and zeta are trade-off parameters which indicate which of the similarities are more important to us here. We implemented this method using eta and zeta equal to 0.5. So we gave an equal weight for each of the semantic similarity and the cosine similarity. We evaluated the label propagation algorithms on the Werner ETL dataset, which has around 14,000 words with valence, dominance, and arousal scores. We rescaled the dataset to minus 4.3 plus 4.3, and we divided the dataset into training, which is a third of the dataset, and testing, which is 2/3 of the dataset. And we sampled the label words or the seed words with the highest EPS score from the training set. And we computed the performance or we evaluated the model on the testing dataset, and we also implemented a supervised learning algorithm trained on that uses support vector regression, and it's trained on the whole training dataset. The result, as showing here, the first part is the count-based label propagation, and the result here is the result obtained using the semantic lexicon label propagation, and this is using the neural word embedding label propagation. The highest performance was obtained using the semantic and neural word embedding label propagation, where tau, the correlation scores, were high for for each EP, were the highest for each E, the evaluation potency and activity. As showing here, the results were kind of comparable to the results obtained from the supervised learning algorithm that uses the whole training set, and it's trained using support vector regression. As showing in the results here, the result of the potency was the lowest among the three dimensions. Here we are showing some examples example that we were able to get using the both semantic and neural word embeddings. As showing here, like injustice using the skipgram and WordNet, we're giving quite close EPA score to the original score or the true EPA in the Werner ETL dataset. Evil as well was giving the result of the EPA score of evil was close to the true value. In conclusion, in this study, we extended a three-dimensional lexicon in semi-supervised fashion. We evaluated the induced EBE lexicon against a manually annotated lexicon, and we evaluated the label propagation algorithm using several word embeddings and semantic lexicons. Thank you for listening.